Welcome all. My name is Matthias Troyer. I'm a technical fellow and corporate vice president at Microsoft Quantum, where I lead the team that works on the applications and the architecture of quantum computers. I've worked in computing for many decades. And what I've realized is that to achieve the ambitions I have, the goals I have, I want to have a quantum computer, a utility-scale quantum computer that can let me solve problems that seemed intractable when I started in computing. And for that, I want to take you on a journey to the edge of human ingenuity, to the boundary, the frontier of science and engineering. The reason why that is possible is that new science has always led to new technologies. Let's look back at the industrial age that was enabled by thermodynamics that led to the invention of the steam engine. Well, then let's look at the Silicon Age, telecommunications, computing, that was enabled by Maxwell's equations, electromagnetism, again, a physics breakthrough that changed the world through new technologies. And 100 years ago, scientists invented quantum mechanics, quantum physics, the theory that describes nature and the behavior of electrons in molecules and materials. And that is starting to change the world now with new technologies like with quantum computers. And you've heard lots about quantum computing, how it will change everything we do. And of course, there's lots of hype around quantum computing, but that is because there's lots of potential. We've worked on quantum computing for more than 20 years, and in that time, we've gotten to the point now where the hype has given rise to clarity. We understand what quantum computers will be able to do, and we understand what is needed to achieve that. First is, what is it that we want to build? We want to build a utility-scale quantum computer. That is a machine that can solve interesting problems that it cannot solve in any way on a classical computer. We want to be able to solve problems that seem totally intractable. But to be interesting beyond that, we want more. We want a machine that is of true utility scale. A machine that can solve a problem where the value of the solution exceeds the cost of the computation to get there. Such a machine will have really broad impact on our society, our life on the planet. To get there, we have to first understand why a quantum computer can solve problems that it cannot solve classically. And the reason why fundamentally it can do that is that it works on very different principles than a classical computer. But first, let me show you what it can do because of this. For that, I'm looking at computational complexity, meaning what is the time I need to solve a problem as a function of the problem size. For many problems, that scaling is linear. That is, to make the problem twice as big, the time to solve it might increase by a factor 2. There are some problems that are harder, where there is quadratic scaling, where the time to solve it grows quadratically with the problem size. So when I double the problem size, the time goes up by factor 4. And then there are the really hard problems, where the time to solve them grows exponentially, meaning when I increase it a little bit, the time doubles. We have no problems on classical computers solving problem with linear scaling, with quadratic scaling. Problem with exponential scaling, they are super tough. The advantage of a quantum computer is not that it makes the solution faster by changing the time I need for one operation. The key reason why a quantum computer can solve certain problems that it cannot solve classically is that it changes the scaling. For example, there might be problems where on the classical computer the scaling is quadratic, but on the quantum computer only linear. So using a quantum computer, we go from the quadratic scaling to the linear scaling. comes down, that we call a quadratic speedup, going from quadratic to linear. And the nice thing here is that the bigger I make the problem, the bigger that advantage is, as you can see. And then there are problems where there's an exponential quantum speedup, and they will turn out to be even more interesting, where classically the scaling is exponential. So we'll soon run into a brick wall and can't solve it from a certain size, but where quantum mechanically the scaling is far better, maybe only linear, that we call an exponential quantum speedup. And these problems will turn out to be really important for the application of quantum computing. So what we see here is that when we change the scaling, be it from quadratic to linear, or be it from exponential to polynomial, then we see that when the problem size gets large enough, the quantum computer will always beat the classical computer. But we need one more ingredient to make it practical. To make it practical, I need this crossover time here to be not too long. I need this crossover time to be on the order of a few weeks. When I first looked at quantum algorithms and we looked at the crossover time, then in many cases we realized, yes, there's a great problem of big impact, and there's a quantum algorithm with quantum speedup, and when we implemented it and when we worked out the runtimes, we realized, wonderful, the quantum computer will beat the classical one, but the calculation will take more than the age of the universe. Ouch. That's not useful. So having run into that a few times, we then asked the question, can we get some simple guidelines that help us identify which are the problems where the crossover time here is short enough that the quantum computer will beat the classical computer. Now that needs more than just quantum speedup, because for that, when I want to talk about the crossover time for weeks, then I need to have some constants in there. I need to make assumptions on how fast the classical computer is or how fast the quantum computer is, so that it can actually calculate the time. And for that, of course, I have to speculate. What will we be able to do in the next 10 years? That's a hard question always. So let me make it a bit easier by being super optimistic for quantum computing. And we'll assume on the quantum side, on the right here, an optimistic quantum chip that I can imagine building in the next decade. The type of quantum computer that I dream about having. That will have 10,000 high-quality, error-corrected, so-called logical qubits. And that are very fast, where I can do a quantum operation in only 10 microseconds, so that I can do 100,000 quantum operations per second on 10,000 high-quality qubits. So that's the quantum side. It's my dream. On the classical side, I now need to see what is the competition, what could I do classically. And on the classical side, I'm going to be pessimistic to help the quantum side. And I'm going to assume I take a single one of today's GPUs. In our data centers, we have thousands of them, but let me only take a single one, a single GPU of today compared to what we will build quantumly in the next decade. And how do they compare? The GPUs of today have 80 billion transistors. They're amazing devices. And a time step is only 0.7 nanoseconds. So these are really fast machines. And the current GPU can do 2 petaflop of compute, meaning 2 times 10 to the 15 operations per second. These are amazing chips. Because even my watch that I wear now is faster than the Cray supercomputer I used for my master's thesis. Classical computing has come far. But quantum computing will be able to do even more, will be able to do things that no future GPU-based machine will be able to do. But the quantum computer will not solve all problems. Let's look, for example, at loading data, the I/O bandwidth. Into the GPU, I can load 38,000 gigabits a second. While into that quantum chip that has 10,000 qubits and can do 100,000 operations per second, I can load at most 10,000 times 100,000, that's 1 billion or 1 gigabit a second. That means The quantum computer will be 38,000 times slower in loading data than the classical one. What's the consequence of that? Loading data will be even harder for quantum computers than the classical ones, and thus we want to use the quantum computer for small data problems. They will not help us with big data problems. So, first lesson, let's focus on small data problems. But we know there's this quantum speedup, and quantum speedup means I need to do far fewer operations to solve a problem than classically. However, every single quantum operation is more complex than a classical one. A qubit simply is a much more complex object than a transistor. Thus, the quantum operation will be more complex, will be slower. And when we compare this future quantum chip that I imagine having to the GPU, then I see the quantum chip can do maybe 10,000 floating point operations per second compared to these 2 petaflop or 2 times 10 to the 15 operations per second on the classical computer. So with that now, in order for the quantum computer to beat the classical computer, the quantum speedup we talked about has to overcome that constant difference. Many quantum algorithms that people considered have a quadratic speedup. They're based on Grover's algorithm, a famous quantum algorithm, where we want to find, for example, the best solution among a set of n solutions. To do that, classically, you have to go through all the n options, and for each option I need to calculate a value. On a quantum computer, with Grover's algorithm, I have a quadratic speedup, meaning I can do it with only square root of n calculations of that function. There's speedup, there's a quadratic speedup. But now remember that each quantum operation is slower than a classical one. Still, the quantum computer can beat it, but if the call to the quantum function is 10 to the 11 times slower than the call to a classical one, then in this case I have to make 10 to the 22 calls classically, so that these 10 to the 22 classical calls take more time than the 10 to the 11 quantum calls, where each one is 10 to the 11 times slower. Thus, what we need to get the quantum advantage here is we need n to be a huge number. If the function consists only of a single floating point operation, maybe a single addition or multiplication, then the cost over time is estimated to be a year. So you need to have a problem that takes a year to solve before the quantum computer can be the classical one. Now, a real problem might have about 1,000 floating point operations in the function. With that, the cost of time would be about a millennium. And for a big problem like protein folding, the cost over time approaches the age of the universe. What we learn from that is that we need more than such a quadratic speedup. There's something that we've seen. We need something with a big speedup to overcome the fact that a qubit is much more complex than a classical transistor. If we now go to a quantum algorithm with cubic speedup and want a cost over time of about a week or two, then we can afford doing 3,000 floating point operations. It starts getting interesting. When we get to a quartic speedup, we can afford to potentially do a few 100,000 operations. That's where the interest gets really big. And when the quantum speedup is exponential, then the quantum computer really will beat the classical one. So from all the proposed applications of quantum computing, when we apply these filters that I want a problem that has more than quadratic speedup, ideal exponential speedup, and is a small data problems, then the problems I end up with are in chemistry, in biochemistry, in materials. And why is that? The reason is that just nature, deep down, is quantum mechanically. Quantum mechanics is the theory that describes the behavior of the electrons in a molecule, in a material, and thus a computer built on those principles naturally is well suited to describe it. And that's what Feynman back in '82 meant when he said nature isn't classical, and if you want to make a simulation of nature, you'd better make it quantum mechanical. Thus, he came up with the idea that we need a quantum computer to simulate nature. We can solve so many interesting problems. We can design new materials. For example, we can use it to find the chemical process that removes carbon from the air and undoes global warming. We can use it to find materials that are self-healing. We can use it to find new chemicals that are environmentally safe, new coolants, for example. We can use it to design new batteries, and much, much more. But it will enable it not by itself, but working together with AI and with classical supercomputing. So it's that combination of AI, HPC, and quantum that will really drive the progress. And we've already seen that AI is transforming the way we do science. We've worked on that for years at Microsoft, and we saw it in last year's Nobel Prizes in physics and in chemistry, that the way we do science is changing. I want to show you one example. The team asked the question, can we design a new material with AI? And the challenge they posed themselves was, can we design a new electrolyte for a solid-state lithium battery? And what they managed to do was, in the time of a week, that's the time in which I could have simulated 1,000 known materials, the team could screen 32.6 million potential materials. 32.6 million. That's a large number. And to put it into perspective, mankind from the Stone Age to today has only invented 250,000 crystalline materials. That is more than 100 times more materials than mankind has ever invented since the Stone Age. And with AI, the team could screen these 32.6 million material, found 500,000 stable ones, found 800 suitable electrolytes, 150 interesting ones, then picked out one that looked most promising, took it to the lab, made it, and it worked. What the experts then told us is that's a breakthrough for science, because it typically takes a lab 4 to 5 years to come up with the new candidate. And using AI and HPC acceleration, we could propose a new material within a week. That's the type of change that's happening now with AI. But for that, we ultimately need more than just AI. We also need a quantum computer. To explain why, let's look at problems in chemistry, where the effort to compute something depends on the accuracy. If I want to look at the structure of a molecule or the structure of a crystal, then I can do that with a cheap classical method. I need to basically just look at the forces between atoms and treat them as classical particles. The time to solve that then grows linearly with the number of atoms, and that's a pretty cheap calculation that can be done on big systems. But when I want to have more accurate results, for example, when I want to look at the structure of the electrons within the molecule, then I need to look at the method called density functional theory. I'm treating quantum effects approximately. And then now the time to compute is scales cubically with the problem size. So it gets much more expensive. And when I want to look even more closely, when I want to look at chemical reactions, how bonds form and bonds break, then I need to look even more closely at the electrons, and I need to look at the interactions between the electrons in a quantum mechanical way. And then the scaling becomes harder even with the method called coupled cluster. The scaling becomes the 5th power or 7th power, and ultimately, if you want the best accuracy, I need to solve the quantum problem exactly. And then the time I need to compute it grows exponentially with the size, and that's when it gets really expensive. And that is why Feynman pointed out, to solve these problems, you shouldn't do it on a classical computer, you should actually use a quantum computer. So with a quantum computer, we bring down the complexity of that. We bring down the complexity from exponential to polynomial. We have an exponential quantum speedup. And that's where quantum computers can help. They will help combined with AI. Because people have asked me in the past, can I do protein folding faster with a quantum computer? Can I do density function theory faster with a quantum computer? And my answer is, to accelerate simulations, we use AI. We train an AI model to predict the outcome of the simulation, and then doing the inference call to the model is faster than doing the full simulation. So we make simulations faster with AI. We make them more accurate with quantum computer. And you can guess where that's going. We can combine the two. We can use this more accurate data from the quantum computer to train an AI model that is both fast and accurate. So combining quantum and AI will give us the accuracy of a full quantum simulation at the speed of AI. The way I would do that is I start out with all the classical data I have, with all the data we have already, and train the models we use now already, like the one we used for the battery. And then with the quantum computer, for those molecules and materials where I need more accurate data because the classical data is not accurate enough, I will calculate better training data with the quantum computer. Then I use that to refine the AI model to then get this model that is quantum accurate and fast. And with that model, we can then make accurate predictions for new molecules and new materials. So in some sense, I will use the quantum computer to teach quantum physics to an AI. And what that model will then be able to do is it will be able to predict the properties of materials. And with that, we can then have a big impact on our world, because 96% of all manufactured goods depend on chemistry, depend on material science. You've all used Copilot, you've all used the ChatGPT, you've used it to write an essay, write a letter, create a video. Now, just imagine if you can use the same technology, the same Copilot, but you say now, create a new material with new properties, create a vaccine for a new pandemic, give me a better way of making fertilizer on my farm. That will change the world. That will have an impact on all of humanity. And that's the vision we have for quantum computing. Thank you.